So the dimension of the range of T is 2, because we've got 2 basis elements there. Now let's look at the kernel. So the kernel of T is the set of all A, B, C, negative A, such that T of that is the zero matrix. So that is all of the A, B, C, negative A matrices such that C minus B, negative 2A, 2A, B minus C is the zero matrix. So if that's the zero matrix, then I guess C and B have to be equal, and A has to be equal to 0. So all the matrices of the form, we have 0 here. C and B we said have to be the same, so all the matrices of the form 0, B, B, 0, such that B is a real number. So natural basis for the kernel of the T is just that one matrix 0, 1, 1, 0. We can take any multiple of it. So the dimension of the kernel is 1. And we have that if we add the dimension of the kernel and the dimension of the range together, we've got 1 plus 2, which is 3, which is the dimension of our space V. So the dimension of the space of all matrices A, B, C, negative A. All right, now let's relate this to null space and column space of the matrix of T. So recall that the natural basis of V is the 3 matrices 1, 0, 0, negative 1, 0, 1, 0, 0, and 0, 0, 1, 0. And we computed that the matrix of T with respect to the basis B is 0, negative 1, 1, negative 2, 0, 0, 2, 0, 0. Now, if we set this, we make this a system of equations with 0 on the right hand side, that is, we solve for, let's call this A, solve AX equals 0 to find the null space. Then we have 0, negative 1, 1, 0, negative 2, 0, 0, 0. And we don't even really need that last equation because it's essentially the same as the second to last equation. So this says that x1 equals 0. x3 is a free variable, let's say s, and x2, negative x2 plus x3 equals 0. So it has to be equal to x3, so that's s also. So the null space is all the vectors of the form 0, s, s, where s is any real number. The dimension equals 1, which matches our dimension of the kernel being equal to 1. And the column space, well, has dimension equal to the rank. We can see the rank here pretty easily. I guess we can see the dimension of the column space pretty easily too. The rank is 2. Rank is 2 because we could do one row operation and get rid of the last row here. And we can see that the other two rows are not multiples of each other. So there's no way we could use one to get rid of the other. So the rank is 2. So the rank of 2 plus the nullity of 1 add together to get 3, which is the number of columns in the matrix here. Just like 2 plus 1 equals 3, which is the dimension of the vector space. And by the way, this matrix is asking as left multiplication on R3, another vector space of dimension 3. So this is the coordinate version of dimension of the kernel plus dimension of the range equals 3. The end.